All right, so this is wavelinking, the applied way. Um, you know who we are. So I'm going to start with just a level setting and alignment of what we're talking about. Yeah, I'm going to get to that. Yep. Yeah, we'll get into this. Isn't a real deep dive, just given the time, but it's an overview. I've got 25 years experience in manufacturing and design, and a somewhat unique background in that I've set up facilities from scratch, and where that kind of started was I was working for an injection molder back in the 90s, and it started with noticing that the process was wrong. They were running a part, and it was running 200 degrees Fahrenheit over temp, and I was like, hey, something wrong there, and so I dug in and fixed that. It had to do with the flow channels and the gates and the runners, and it was fixed, ran at the right temp. Next thing I knew, come a few years later, I was setting up mold making for them and designing their products. And from there, that was the first mold or product that I designed for molding, and the mold ran 200% faster than a company that had been doing it for 30 years. And so that just kind of, I didn't even see myself going there. It just all fit in place, it kind of just happened. And so I've set up many facilities since then, and it's been fun. I love it. I love design and manufacturing, and it's allowed me to touch everything. So it really helps when I'm working with customers. I mean, I've set up for that company, set up the ERP and connected the inventory systems and made it, so we didn't have parts running out when the year was busy and overstocked when nobody was ordering them, so just working out those details, programming the molding machine, so process, setting up the designs, automating the designs for the product and the molds, and further down the line, working with robotics, CMM, so inspection, so just kind of end to end, which has been fun. And it also just means that when I come in and work with a customer, I'm kind of seeing all that. I'm seeing the part and how that's going to affect something downstream, or where we can capture data for a process downstream like manufacturing. And so through this career, in about 2005, I had been using SolidWorks Certified Expert, and was then setting up a facility for motion control, so encoders, where we would design the product and the mold and manufacture everything in-house. And SolidWorks just wasn't cutting it. It was, complicated when it came to, like we're going to discuss here, transferring data or linking data between assemblies. I found that I had to have configurations to control it, and a configuration meant that it added complexity, because every feature could have multiple states, however many configurations you had. Every dimension of a feature in the sketch, every dimension in the sketch could have be linked to a configuration. So when there was an error in the tooling assemblies, which could be quite large, it was hard to find. And it came about Siemens, partially because we were manufacturing, using all manufacturing processes, so EDM, screw machines, mill turn, horizontal milling, multi-axis. I was like, what can do everything? And so that was one of the reasons we went there, and didn't realize the power in the design. But wavelinking became a big reason to go with NX, purchasing NX, and the power of that, and how well it worked. And so ever since 2005, every facility or every role I've been in, it's NX. And I've had the choice to buy others, but it's always been NX. And so that kind of came, I bought from a company that ended up partnering with Applied back then, and then later ended up working for Applied previous to now. when it was combined with another sister company and set up their shop too, where we would inspect gauges from castings, and I would CMM inspect them and 5-axis machine them. And so, that kind of gave me a look into the CMM, a deep look into the CMM world. And then previous to just coming back now, I was VP of tooling for a packaging company that had 200 million in revenue, so that was fun. And we took through using wavelengths, I designed an assembly where we took the tooling from 2 to 3 months down to 4 to 5 weeks, and so we were beating everybody in the industry, and which made us, very successful. But yeah, I'm glad to be back. I love working with customers, partnering with them, trying to improve things for them as I did for those companies. And I don't understand every industry and every product, but I understand that it has to be designed and manufactured, and it has to have good quality, and so I'm able to figure it out quickly and learn by working with the customer, and they share their knowledge and I share mine. So wave linking is just like I said, it's part of the power of NX. It's really an advantage that I've seen unlike any other software, or not as good in other software. And so, but there's issues with it if you don't use it correctly, and so that's what we're going to talk about today. So our customer, we've seen issues. They don't, even us, we didn't necessarily know right away in some of the cases that it was wavelengths, but the issues were reported as major problems. Sometimes not your memory error, but your PLM, XML, or just crazy errors, and then slow, unresponsive assemblies opening. In some cases 2 hours to open it, and then come to find out using the wave linker, as you can kind of see the preview here. Or not the wave linker, can't think of the name right now, the relations browser. You can see how the relations are how the flow of the wavelengths are, and so you can really diagnose it there. But what we found was there was just way too many cases where bolts are being wavelength, things that don't change, circular references, cross links, so just a spider web. It just looked like, it's crazy. So the solution was simplifying that and then getting it right, and took the load time down from 2 hours to minutes. It's not that easy though. I mean, so we'll go through that here. This is kind of just an overview, it's a best practice, but it's, the why and the how. It's kind of just the tip of the iceberg, because there's just a lot that goes into it. We have to look at, your process. So this is, just gets into the use case and, what thought needs to go into it. And so what is wavelength? For those who don't know, it's an out-of-the-box capability to take geometry that's going to change, dynamic geometry, and distribute it from one file to another, so that the things, the components that need to see that change and update will see it. And so in this case, basically the face of this inlet, a fuel inlet, is the only thing that needs to be copied over instead of the whole body. But the important point here is it is only for geometry that changes, not static geometry. Use copy and paste if you're going to just transfer something that you want to see in another part or an assembly. So, to understand what structures we'll use to create the wavelengths, we need to understand what a top-down assembly is. It's a system that defines components. So in this case, it's maybe the exterior of the airplane, and that's defining the rest of the assembly from the top down. The other components will update based on that. It's really just going to be the parts that you're designing that are changing and that you want to have So it might include other, of course, other parts that you're designing, but whatever you're designing would be in the top level. And then whatever it relates to or it will update would also be in there, but not everything. It's a small part of the BOM. It's definitely not a complete BOM. Bottom-up design is components that define a system, and so this would be where you'll put everything together after it's been designed in the top down, in that reduced BOM. You would bring it in here and put everything together. So I think of this like when I had my wife's Subaru parts all over the garage floor, and the car itself is already defined, and I'm just assembling them into the defined system. And so there's no change. You're just putting everything together, and this is where we'll get more into the use of this. And so now we'll take a look at goals. And so what we're looking at, and then the goals. Here we want control of the dynamic geometry. We only want the intended wavelengths, and we want kind of that nice waterfall flow of information from the top down. We want to avoid the circular loops, and really this comes through a defined hierarchy where you've thought it out, and you can have that kind of a controlled flow. Part of the is to consider what is a good fit into wavelengths, and we got to think about is this really a good product, or what can this be used for in the future. And so in the case where you don't want to take something like your system and take a small coupe into a medium-sized pickup. And so you want flexibility in your system, but you don't want to break it by not thinking out and thinking about what is the primary input, and what is the anticipated change. So what's a good candidate and maybe a poor candidate. And this isn't always going to be, these are just examples. In some cases, a foam might be a good candidate. But we want to make sure the product is functionally driven and defined. So methodologies, talking about the methods here. Design the upper levels of the top-down design structure with the intended user skill set in mind. So a lot of times what I do with this is just a clearly defined structure, naming. I think of anything when you're putting an assembly like this together, you want good UI. If that UI is the feedback of what's happening, that comes for me through naming and organization, so that people, when they open it, they understand. And I think a big part of that is, creating some kind of standardization in your naming of features or wavelengths internally, to try to, instead of everybody naming features and naming even any part of the structure, just willy-nilly, you want to definitely define that and try to make it something where it will help them understand. It could even be colors, tags. There's a lot of different ways to do that. And then proactively coach and mentor the users on the structure that you've defined, and publish that as a user guide. Of course, just as this system will be iterated and improved over time, initially it might start your defined structure that you're reusing, hopefully, might start out not so great. It might have issues in the beginning, but as you iterate that, if you're reusing that structure, you can make those improvements over time. And then of course update the documentation and coach often. If when I'm doing these systems, if I discover something new, a new feature, a new something that's been released that's helpful, or I just discovered something new, I'm going to share that with the other users and document it. And then we're going to want to limit the access, to this system. So that's where it comes into looking at, when we talk about breaking down the structure, it does also matter, your groups in Team Center, your groups within your company, and the permissions they have. But you want to lock it down to above average users and as few as practical. The rest should be just owning the components. And then the top down, you don't want the enterprise consumers having access to that. So that could be, purchasing or anybody that's not designing. When you're creating the structure of your top-down design assembly, you need to start here, start with the whiteboard, start by the planning. So this is a very crucial step. It's one of the most powerful, is thinking it out instead of just jumping in. Do this before opening NX and, define your groups. And if they're not something you already have in Team Center, then get those into Team Center so you have the right rules. And consult with the design SMEs, get their input. Don't do everything at the top. You want to reflect your top-down design intent driver and driven relationships in the assembly hierarchy. You want everything to be, most changes should be happening down low. And the drive part is the wave source. And then the driven part is the wave destination. So in this case here, if you're purchasing the motor but designing the mount is the driver and the motor is driven. So it'll change position based on the drive. So based on what you're defining. And there's, usually at least one flexible component. This is another key area where we're seeing another breakdown of the wavelength structure when we analyze it through the inner part relations browser. Some of these look like the nervous system, as I said, just crazy, not a nice flow like this, jumping from maybe from this assembly here back and forth, and that's really what extends the load times, because you have information jumping across assemblies. It means when you open something, if you don't have the right load options, you're going to open too many things. And so that's a real time killer. So you want it to look, again, like a nice waterfall. Don't skip assembly tiers. Don't link across assembly nodes, and avoid creating wavelengths in the bottom-up design. Here's another example, another view of the relations browser. This one looks a lot better. This looks good. The other one, I didn't want to zoom in too much, but it was crazy, really bad. But this will tell you if your wavelengths are being properly used. It's under assemblies, and then in the wavelength area, it's in the drop down there. But for those that need to know, analyze it. Use this, but monitor and police the structure. Have someone in charge of that assembly, and in charge of going in and seeing if everything is staying well maintained and not getting too crazy. And coach people, keep just, don't leave it alone or it'll become messy. It's like leaving someone, I don't know. Letting your kids mess up their bedrooms without checking in, it becomes a little too crazy, and you don't even want to go in there. And then, just again, do your wavelengths in the top down. So just summarizing, this is where you want to do it, and make sure that you're only doing the parts that you need to have in here. You don't want everything in here. You don't want to overload this assembly. You want to keep it simple. And the bottom up structure is just where you're going to bring everything together so that you have a complete assembly. And of course, that's important to have your complete BOM for purchasing, for manufacturing. So what we're getting in here is just keeping things light, some tips and tricks on keeping things light. Oops, one too many. In this case, you could have wavelengthed the whole body, but you don't need to. The portion that's changing is just on that face, the location and size of the inlets. So just do the face by itself, and then avoid linking interactions with other confusing, conflicting, complex interpart relationships, example, expressions or assembly constraints. You want the minimum data as possible. Some tips for reducing load times and reducing, every time you make a change, you don't want to wait for that change to take effect throughout the assembly that you have open. So delay link update, that's going to save you a lot of pain. Otherwise, you're gonna, every time you change something, it's going to be thinking and processing. This is a big tip that I haven't always thought of because some of the assemblies, it's not as necessary if they're not very large, but context independent. And so this is basically not transferring the position of the component. It's just the geometry. And so this is a big load on the system, because if that position is, outside of, or depending on how many levels it is away from that part, it's got to open and look through all those levels and get that positional data. And it also means if you don't open enough, you might not be up to date. So by making it independent, you don't have to worry about that. You have the geometry up to date, but the position is locally defined. And when you do, when you're going to make a change or you're aware of something that has changed at the top, you want to work through the structure. And so this is where someone in charge of the assembly who's responsible for it is going to, go and take care of this, and they're going to have permission to do this. So they want to go from the top and just work the way down and make sure everything's up to date. Persistently freezing wavelengths. This is, according to some contacts I have at Siemens, even lighter than breaking, and you don't have to go back and fix it. Breaking is when you click the associativity off. There's still some information that goes when you break, or can. It's looking at the history, where persistently freeze is supposed to turn off any method it has of looking at the history of that wavelength and where it did come from. And that's an option, that we can guide you on, or if you look up that functionality in the documentation, it'll show you where that's at. And
that feature only available on free.
Yeah. So that's where the person, again, so the person in charge. You wish it was down available in a lower tool.
That way you can tell your engineers before you release the part, you freeze your release rather than having someone be responsible for that.
So it might not be a good fit for everyone. You could do, in that case, the broken. It's pretty similar. And then release from the top down, and then alert component owners that there's been changes and that you're releasing. All right. Good. Okay. So I'd like to say, thank you to Siemens, Jim Forrester at Siemens. He provided this information, a lot of it. He's really a subject matter expert in this area as far as how to communicate it. I'm very knowledgeable of wavelinking, but he's had a lot of experience over the years communicating about wavelinking and helping people understand. This demo is an example that he had an intern put together over the summer with some coaching. Let's see if I can get it to play here very carefully. All right, so this is basically defined, there's a top-down structure, which we're seeing right now, and the payload diameter and weight is what creates the update on the bottom up. So this is the assembly with all the details that you're going to see the end result of the update. And so he's updating the top down, but those updates are rolling through to the bottom up. And so you can see all the stages being updated. And so, imagine the time savings if, you have something well-defined like this, and you need to, again, increase payload. You're coming out, with a new rocket, and you want to take, larger satellites into space. You can start from scratch with something that might not work as far as transferring the updates, or you can start with something is going to successfully, transfer that information and cause the downstream updates. Huge time saver. I mean, and I think a lot.
That's to do with the Fly CX rocket, is that what that is?
Yeah, we're gonna fly it for sure. So yeah, just understanding the goals, understanding the do's and don'ts. Just giving, this was to give a guide. There's just too much to cram into this time. Hopefully it was enough guide that gives you some questions, general recommendations, and something to think about. But we can, work with you to help take this and put it into action.